Hi, everybody. This is from page 26 of your unit packet. This is kind of a unique lesson. There are several different key levers involved in our review topic for tomorrow. So I'm going to probably have to chunk this into two videos, do the first three key levers and then the second set in another video. So follow along, take notes as usual, and come to class prepared to show me all this tomorrow. So our first key lever is the limit definition of the derivative, or derivatives in disguise. The model problem defines our function for us as sine of 2x, and we're asked to evaluate this limit as x approaches 0 of f of x minus f of 0. So one way that I've shown people how to do this in tutorials is using L'Hopital's rule, because with a quick substitution, you can see here that if I plug in a 0 into this limit, I'll get f of 0 minus f of 0 up top and 0 minus 0 on the bottom. And taking the derivative is a great way to adjust for that. But what I want to talk you through in this quick segment is just how, when we first learned about derivatives, one of the key definitions that defined our derivative format was the limit as x approaches a of f of x minus f of a all over, that's an f, sorry, x minus a. So if we can remember this template for a derivative, then when we see some of these limits, we should actually recognize that they meet this criteria and are just requesting that we calculate the derivative of our function. And actually, hold on, let me make sure I'm being accurate here. That x right there, I should have put an a. This is the limit definition of a derivative at a specific point. So what this is really asking us for, if I highlight this limit that's being requested, is for me to take the function that's been provided and calculate its derivative at the specific a value in question. And if you link up all of the pieces of the original definition with our problem, it looks to me like this value of a that's showing up in my definition is being replaced with a 0 back here in the limit for this model problem. So what I want to try and do is just uncover what the definition of f prime of 0 is equal to in this problem. That's all that this limit is really wanting me to compute. So let me see. Well, to find f prime of 0, I need to slow down and find f prime of x. So the function sine of 2x, sine we know goes to cosine. We've been talking a lot about derivatives lately, so I keep 2x intact and multiply by 2. If I can plug a 0 into this function and dig through a little bit of trig, I'm going to have the answer to this limit. I went ahead and multiplied 0 by 2 inside that trig function to simplify, and I use my unit circle. Cosine of 0 is 1. 1 times 2 is 2. No limit, no nothing. If I recognize that this is a derivative problem, it's as simple as that. Okay, so key lever number 2 is in fact more specifically geared toward L'Hopital's rule, which I've highlighted here in the box, just recapping what the rule itself states. And then I have 3 examples here. I'm only going to talk you through one, and I'd urge you to pause the video and try the other 2 before you come to class tomorrow if you have time. I'll probably do the second one since that looks like the trickiest derivative. But L'Hopital's rule states that if you have a limit of the ratio of 2 functions, so if you're looking at this limit right here as x approaches c of f divided by g, and you get an indeterminate form, then that limit is actually equal to the limit of the derivative of the function on top divided by the derivative of the function on the bottom, the ratio of the derivatives. So what we want to do, what we want to do when we are looking at some of these limits is ensure that we're trying direct substitution and verifying if we get an indeterminate form, instead of having to do a lot of algebra that maybe we tried at the beginning of the year, we can just use a quick L'Hopital's rule and run through the problem like that. So I'm going to try and be pretty formal in my notation here. This is something College Board's been pushing us on lately. I used to just come up to the limit and say equals 0 over 0, oh no. And I got some feedback from a friend of mine the other day that that's actually not proper notation. So I'm going to do example 2 right now. And here's what I want to show if I'm going to do L'Hopital. I want to write, oh my gosh, I don't know what I just did. Okay, here we go. I want to write the limit as x approaches 7 of the numerator. I want to say the limit as x approaches 7 of x plus 2 minus 3 equals, and then do some substitution. This is going to be 7 plus 2 underneath the radical minus 3. Do some mental math, I get 0. That's one line of pre-work that has to happen. And then separately, I want to show the limit as x approaches 7 of the denominator, x minus 7. Do direct substitution, and I get 0. Instead of doing what I've done in the past and just plugging in and writing 0 over 0, I want you guys to split up your numerator and denominator like I did right here, and then off to the side say, okay, because I get 0 up top and 0 on the bottom, L'Hopital's rule applies. That's a standard setup that I want to see from you, and it's something that I just found out College Board is requesting of us. If I can do all that, then I'm going to come down below, and since I've determined that L'Hopital's rule applies, I'm going to actually show the reader that I know what L'Hopital's rule says I can do. The rule states that I can take my ratio that I started with, and instead of comparing the original two functions, we can compare their derivatives. I'm going to start with the bottom. That looks easier. X minus 7 has a derivative of 1. And based on all of our recapped rules of derivatives from our recent lessons, square root of x plus 2 minus 3 has a derivative of 1 over 2 square roots of x plus 2. That minus 3 has a derivative of 0, so I don't need to write anything. And now I can plug in, and it looks like I have 1 over 2 square roots of 7 plus 2, or 1 over 2 times 3, which results in my final answer of 1/6. So the new piece here that I really wanted to highlight is that top couple of lines where I split my numerator and denominator up and state that I'm using L'Hopital's rule. So we'll be using that format now, and I'd recommend you try example 1 and example 3 before going on to the next key lever. Okay, so key lever 3 is on related rates, and this is traditionally a very, very difficult skill for students, one of the harder topics that we've learned this year. It involves a word problem where our typical variables are not the only things to consider, but time is also something that's really important in these kinds of problems. So here we have a hemispherical water tank that's got a radius of 6 meters, and this tank is losing water. So the area of the surface of the water is provided to us as this function A equals 12 pi h minus pi h squared square meters, where h is the depth in meters of the water in the tank. I'm going to keep highlighting important information. When h is 3, the depth of the water is decreasing at a rate of 0.5 meter per minute. At that instant, what is the rate at which the area of the water's surface is decreasing with respect to time? So there's a lot going on here in this problem. I see a formula for A that's given to me down there, 12 pi h minus pi h squared. I see at the very end, the request in this problem is to find the rate of that area. So the rate of area with respect to time. We've looked at this in some format in our implicit differentiation conversations. That's asking for dA over dt. Some other stuff I know is that, all right, sorry about that. If we go back to the problem, we're also noticing here that h is defined for us as 3, and then there's this other quantity of 1/2 that I have to figure out a value to, I need to figure out a name for that value. The 1/2 is measured in meters per minute, and the verbal description here provided says that the depth of the water is decreasing at that rate. So another word for depth in my mind, and especially when I have this image here, is height. But I already have a height value of 3, so then I have to dig in and realize, wait, this is not a height of 1/2 that they're giving me, it's the rate of that height. And rate, we've talked about this a lot, is another word for slope, which in calculus represents derivative. So what they're giving me here is that dH dt is decreasing at a rate of 1/2. It's really easy to just label that with 1/2, but I want you to be extra careful because that word decreasing means that that rate is negative. Okay, so here's all my known information, and I want to try and find dA dt. Well, dA dt is very specifically linked up with the area formula that we've got, and I know from A to dA dt, I'm just taking a derivative. So if I want to find that missing quantity, I'm going to have to start by taking the derivative of A. So I'll come down here and do that. The derivative of A in really fancy notation is dA dt equal to derivative of 12 pi h. That's 12 pi. That's a constant on my h. But because h is changing with respect to time, I need an h prime after that derivative, or a dH dt. Minus, let's keep going, pi h squared. If the pi wasn't there, h squared would have a derivative of 2h. So the pi is there. That means I've got 2 pi h. And then again, h has a derivative of h prime. So I have to tack on the dH dt to that product, that power rule that I just did. Okay, so now I get to sub in because every quantity that I have here is defined in all of that work that I did up above. This problem becomes 12 pi times dH dt, which I know is negative 1/2, minus 2 pi times my height of 3 times another dH dt of negative 1/2. Do a little bit of math, I get negative 6 pi for the first term, minus, let's see, 2 times 3 is 6, half of that is 3, but my two negatives actually make a positive, so I think I want to add 3 pi's for my second term, and then combine like terms, that's negative 3 pi. This is a value for dA dt. Remember, that's what I was finding. So my units are going to be area per time. Area in this case is square meters, and my time is minutes. So we're going to get a lot more practice with this big key lever because this is a very difficult skill. And all right, I'm going to end this first video and then come back on in a second for the remaining key levers. So take a break if you need to, and then pop back on and watch the rest of that when you're ready.